It's my pleasure to be here. Uh, so, okay, so to understand the scene, we are faced with several different problems. So sometimes we want to infer the label for each pixel in the image. For example, this is like a tree pixel, this is a building pixel, and so on and so forth. And sometimes we want to go beyond that and count the instances of a particular object category. For example, I see like 10 cars in this image. Or we want to estimate the type of the scene. For example, this is a street scene and the weather is partly cloudy. Or we want to estimate the direction of the movements of the object. For example, the person is coming toward the camera and the cars are going in that direction. Or we want to estimate the ground plane and walkable surfaces or structures perpendicular to the ground plane. So in this talk, I will focus on 3 specific subproblems. So the first part of the talk is about semantic segmentation and object detection. By semantic segmentation, I mean inferring the pixel labels, and by object detection, I mean localizing and counting the objects. And the second part of my talk is about contextual reasoning. So using the context information to do scene understanding. And I think the same concept exists in the NLP area. So you use the context in the sentence to resolve the ambiguity for a word in the sentence. And finally, I will talk about our recent work on 3D pose estimation and subcategory recognition, which basically provides richer descriptions for objects. Okay, so the first part of the talk is about semantic segmentation and object detection. So here is the output of one of the state-of-the-art segmentation methods. So as you see, the output is more or less reasonable. It makes some mistakes, but generally it's okay. These segments, sometimes these segmentation methods fail. For example, if you have 2 instances of the same category next to each other, the segmentation method cannot really separate them. Or in this case, because the color of these branches is similar to the color of the bird, so it makes a mistake and thinks the bird is, this is the box for the bird. And this particular segmentation method is based on some sort of thresholding. So if no segment passes that threshold, you don't see any segment in the image. So here we propose an approach to recover from the mistakes that each task makes. I mean, the mistakes of detection and the mistakes of the semantic segmentation. And so we formulate the problem as MRF inference. And so this is the first term is the appearance term. So basically, it means this phi is a feature. It can be any feature. So in this work, we use like histogram of gradients, but it can be any other features. And the model that we have is basically a star model. So we have a template for the object, and that template is connected to a set of parts. And basically, we loop over all of these, all of the template for the full object and the template for the parts. And this is a deformation term. Basically, this captures the displacements of the parts with respect to the object. So this is kind of has become kind of a standard thing in computer vision, and so here we added an additional term, which is kind of segmentation term. So we want to incorporate segmentation into this framework, and H here is a latent variable that basically specifies the segment. So the segment can be any segment in the image. If H is equal to 0, it means that no segment is selected for that particular object. So in the next couple of slides, I will talk about how we compute this term here. And this orange area is the segment that I just mentioned. And this blue area is the bounding box. So our object detector is a sliding window detector. So we need to go over, so we have a window that goes over the image, and also it checks all different scales. And so this blue area is one of those bounding boxes. So we check how many pixels of the segment fall inside the object bounding box, and how many pixels of the segment fall outside the object bounding box. So that's one feature that we use. And similarly for background, so we check how many pixels of the background fall inside the object bounding box and how many pixels of the background fall outside the object bounding box. As I said, we need to check all the positions and all the scales, and we need to be efficient. So we need an efficient method to do this. So, and here we use a trick called like integral images. So this is the segment. This is the corresponding integral image. So integral image basically is each point is this. For example, this point here is the sum of everything on the top left of that pixel. And so we can read just simply 4 numbers and compute the features that we want. And this so we can compute the features for all possible positions and scales in constant time. So we have also 2 additional features. One is like the overlap between the bounding box around the segment and also the object bounding box. And also we have this background bias. So sometimes we do not want to select a segment, so that in that case this term is activated. So in terms of qualitative results, so this is the ground truth that we have for detection. This is the segmentation method that the output of the segmentation method that we use. For example, there's a mistake here for detecting the bird. And this is DPM, which is kind of a standard object detection method in computer vision. So for example, and the last column is our method. So in this case, the segmentation method makes a mistake, and DPM doesn't have any idea where the bird is, but we can basically put a tight box around the object. So in terms of comparison with other methods, so this is our method. We basically outperformed the best previous method by 4%, which is kind of significant for this particular data set. Okay, so the next part of my talk is about contextual reasoning. So maybe I can better motivate this part by this example. So can you recognize this object?
It's a bird.
Any other guess? Okay, so here, so this is the car over there. So as soon as you see the contextual information, you can easily recognize that object. So, and how about this one? This is another example. So, okay, so this is also a car which is parked here. So again, so my argument is that for recognition, reasoning based on pixel is not enough. So as soon as you, object pixels, and as soon as you see contextual information, you can reason about the object and recognize the object. But there is also a counter argument and for context. So I can put this cat anywhere in this image, and you can recognize it reliably, irrespective of the context. So we need to learn when we should rely on object appearance and when we should rely on the context. So if the object appearance is good enough, maybe there is no need to rely on context. So okay, so for this task, so we required a suitable data set for context. So we augmented Pascal data set with 500 additional categories. So Pascal is one of the challenging data sets in computer vision, but it only has 20 object categories. So we augmented that data set with 500 additional categories, provided other labels. And so these are some context classes like sky, water, grass, and so on and so forth. And we decided to remove some of these categories. I mean, by remove, I mean ignoring them. And the reason was that the performance for detecting these categories was very bad. And for example, the the performance is 1.7%, which is not really useful. So we ignored these objects and okay. So here is our context model. Sorry. So here is the object so the object, the red box is the object captures object appearance, and also we have 4 boxes around the object that capture context. So, so these boxes can move around so the best location is found for the contextual features. And as I said, similar to what we had before, we have a term for appearance, which is the object appearance. We have a term for part deformations, which basically captures the displacement of the parts with respect to that object. And also another term that we have is the local context. So by local context, I mean the context, the immediate surrounding of the object. For example, here we have a classifier that tells us that, for example, on the top part we have 90% sky, and like the bottom part is I don't know, 100% road, and so we have a classifier that tells us this information. And so this is one of the feature vectors that we use. And also we have a global context. So by global context, I mean if that particular category exists in the image or not. For example, do I see the sky in this image or not? Do I see grass in this image or not? So that's basically a binary feature. So and we use that to capture the scene level context or the global context. And also we have this context deformation, which basically captures the displacement of these context parts with respect to the object.
Quick question.
Yes.
So how do you model your confidence in the recognition of the object? Are you saying that you're going to rely on the context less if you're quite sure? But I don't see where that's coming from.
So here is kind of so when we do learning, so we learn these weights. As an example, humans can appear in any context. So in that case, the weight for all of these terms go down, and the weight for the appearance term goes up. So in that case, it says, okay, so I will rely more on the appearance of the object, not on the context. So because humans can, any category can appear around a human. So that type of thing. Or if my appearance is weak, and so I get a low score for this term, but these terms are strong, then the score for the total score goes up for that object. Does that answer your question?
So the confidence that you're looking for is the appearance segmentation. The first W transpose the phi is basically the confidence score on the top. We call it appearance.
So,
Good question.
yeah, sure.
For the local context, you use like the real numbers to represent what fraction is sky versus.
Yes.
And for the global, you use just 0, 1 binary. Is there a reason?
Yeah, that so global is kind of scene level. So you can basically assume that you have a box for the full image and check if that category exists in that box or not. So maybe the percentage of that might not be too important. So just the presence or absence might capture what you need. And so, for example, if I see like 50% of sky or like 80% of sky, might not be very different in terms of global context. But so the binary feature might be better to represent that.
Along that question, so now you have an objective function which is a mixture of real numbers and binaries.
Yes.
How would you optimize it?
So basically, it's the same framework. So that's we don't do anything special for that. Just we have this. These weights can be any real number. So. Okay, so here there are some results, and so for example, the appearance for the boat is very weak, but when we have context, it says, okay, so I see water at the bottom and the sky on top, so that little thing over there should be a boat, and so we can kind of localize that. And also we have divided the objects into 5 size categories, like extra small, small, medium, large, and extra large objects. And it seems that the context is most helpful for extra large and extra small categories. And because when we have very small objects, the appearance is weak, but context helps to boost the recognition performance. And
what is your intuition for very large? Because I would assume that if the object is very large, there's not much other context.
So those objects are kind of truncated and or occluded, and so in that case, the appearance is very weak. So if you see just a little bit of context around the object, you can boost that. You can basically compensate for the weak appearance of the large object. Also, we tried that for, we augmented one of the state-of-the-art segmentation method, this O2P, with just very simple contextual features, and we improved that performance by like 0.5%. That's a kind of a minor improvement, but it corresponds to like millions of pixels in the data set. So to conclude this part of the talk, so context is a good cue when the appearance is weak, and for example, the tiny objects or occluded objects, so we do not have a strong appearance for those. And sometimes context is confusing, so it can increase confusion between semantically similar categories. For example, bicycle and motorbike appear in the same context, so that using context might even increase the confusion. And so we use very, very simple context features. So we expect that encoding higher level context information can improve the results. So the last part of the talk is about 3D pose estimation and subcategory recognition. So by 3D pose estimation, I mean we want to know the viewpoint of the object. We want to know where the camera is located with respect to the object. And by subcategory recognition, I mean we want to provide detailed information about the object category. For example, not only we want to say this is a car, we want to recognize the actual subtype of the car. Is it a Ford? Is it a Toyota? And so on and so forth. Okay, so why we need 3D pose estimation? Suppose an example is you have autonomous cars. So to operate autonomously, they need to know that the location of other objects and orientation of other objects with respect to this car. And another thing is that the 3D sensors, RGBD sensors, have become very common these years. But what they provide is just a depth map. They don't provide any semantic information. So here we need some sort of pose estimation so we can augment this type of data and assign semantics to the depth map that we have. Or suppose you have an agent that wants to cook food for you. It needs to know the orientation and location of all of the utensils and so on. Or why we need fine grain recognition? So this is an example found by my colleagues. So there are two different type of cars. Like one is like 2010, and the other one is like 2012 model of that car. The only difference is just this front bumper. So that really needs an expert to tell us the difference. So if we can automate that, so we can basically eliminate the need for experts to do this type of things. And suppose also you have an agent that wants to work with these refrigerators. So these are two different types of refrigerators, and the agent needs to know, the robot needs to know the exact type of the refrigerator so it can work with those properly. Okay, so here is the model that we have. So we have a coarse to fine model. The top level is just a category, a basic level category like car, boat, airplane, and so on and so forth. And the fine level, I mean the second level is truck, sedan, race, different types of cars. And as we go down the hierarchy, we add more detailed information about the object. And for example, the lowest level is like Benz, Toyota, Ford, and these different types of sedans, for example. And so our model is based on a combination of three things. So we use 3D CAD models, which basically a mesh that has like vertices and faces and represent an object category. We also have used this deep learning features, the features that are computed based on convolutional neural networks. And also we have global 2D shapes, which is based on these histogram of gradients, which is one of the common features. Yeah, the taxonomy is designed by hand, so that's. But there exists these categories like WordNet or ImageNet, so they have this taxonomy, and you can use those instead. Because we were kind of limited by the CAD models that we had, and so we had to be careful like what categories and what we want to use in. So here's the model that we have. So the top level of the hierarchy is this just captures discrete viewpoint, which is a very coarse information. By discrete viewpoint, I mean, for example, front view of the car, like side view of the car, just a set of discrete viewpoints of the car. And the second level of the hierarchy is so we have the discrete viewpoint, but we also have continuous viewpoint. So the continuous viewpoint is basically provides the depth, it provides the azimuth and elevation. So by azimuth, I mean the angle around the car. Elevation is the elevation of the camera with respect to the object or car, or in this case. And also we have a variable that captures the subcategory information. So it's a random variable that takes values like sedan, race, truck, and so on. And that the finest level of the hierarchy is has also continuous viewpoint, a discrete viewpoint, and subcategory information, and also finer subcategory information. And the problem here is that we have a mixture of continuous and discrete random variables in the model, and solving this might not be straightforward. So we used.
Do you do that within category, or is this also across category?
What do you mean?
When you deal with this factor graph, this is only for cars. Because I don't see a node for.
Yeah, I removed that. There is a node O which captures the object category, right. So that O can be like car, boat, or something. So this particular graph is for one category. Yes. And then so here we use an approach that shares similarities with this particle convex belief propagation, which samples from your continuous viewpoint, continuous variable. And so after sampling, everything becomes discrete, and you can apply the common techniques for discrete MRFs, and you can solve this learning problem with discrete structures. Yeah.
Could you also comment why F is only connected to V3 and not V2 and V1?
So F. So we have this pairwise constraint that imposes this constraint that V1, V2, and V3 should be equal. So just to make the graph more intuitive, we divided those into three different nodes. But you can collapse all of them into just one node. So that this pairwise edge that I didn't talk about. So that basically enforces that constraint. So here are some qualitative results, and here we have this kind of sheep, and what you see here is the projection of the corresponding CAD model according to the estimated continuous viewpoint. And so it can kind of detect the type of the object. So so you can see the viewpoint of the object and also the subcategory of the object. So this is like airline, airplane. This is mini, and so there are different examples. And in terms of quantitative results, so this is the state of the art for pose estimation. So we have 5 different type of evaluation. Bounding box is just evaluating the bounding box if we have identified the bounding box correctly or not. Viewpoint is we check if the viewpoint is estimated correctly or not, and also subcategory and viewpoint and subcategory together, and all means all of these tasks like viewpoint, subcategory, and finder subcategory. So, and as you see, it's a pretty difficult task, and our method obtains like 3.2%, which is kind of pretty low. Just note that the chance is very low. The chance is like 1 over 400 or something. And also, we have here the flat model of aversion. Suppose you collapse the hierarchy into a flat model instead of having that coarse to fine hierarchy. So this table shows that we also improve over the flat version of our model.
Do you have a sense, like the improvement over the ECCV12 paper? That's a pretty big improvement. Do you have a sense how much of this we should contribute to the better feature, the CNN feature, and how much of it should contribute to the model?
So, yeah, the main source of improvement is the CNN feature. But so here for the flat model, we also use the CNN feature. So probably this improvement is for CNN feature, and this improvement here is is attributed to the model. Yes.
I have a basic question here. So you describe the 3D pose estimation together with subcategory recognition. I see the second thing, subcategory recognition, just has a refined version. You just have more categories than cars. So is the first thing doing something like that? Just treat minis and sedans and everything as separate categories? I guess the 3D stuff, is that just a new feature that you're using to handle these refined categories, or is there something fundamental need for this?
Okay, so for example, if sedans seen from a particular viewpoint, they form a very tight cluster in the status space. So for example, if you have like side view of sedan and back view of sedan, they're totally different. So they cannot belong to the same cluster if you do clustering on these images. So basically, estimating viewpoint and subcategory together helps us to capture this type of information. For example, if like like side view sedans are very similar to each other. Side view race cars are very similar to each other. So that basically helps us to better cluster these images together.
Let me rephrase my question. Could you then do the same thing with like side view of cars will look much similar to each other compared to side views of trucks or side views of bicycles? Could you do the same 3D pose estimation at the category level rather than just the subcategory?
Yes, we can do that at category level too, but there is too much variation in the category level. For example, the race cars are totally different from trucks, and so that so if we go to the subcategory level, maybe we can better separate those. And because if you have a like single model to capture both both types of cars, then it might be too much for that model to handle all of these variations. Yes.
So the CAD models package would be specified a priori, and sort of the contextualizing information in the previous part talk, those also had to be sort of specified. Like maybe we care about street, maybe we care about clouds. Although, like an example you had where it's very sunny, and so it's hard to recognize the car. It seems like there might be other pieces of information. So I guess the question is, how feasible would sort of an unsupervised approach to look over a whole bunch of images and try to deduce the reasonable CAD models or some description of what models are, or look over a whole bunch of images and try to deduce what reasonable contextualizing information is? Is anyone looking at that?
Yeah, that would be very interesting to do all of these in an unsupervised fashion without any supervision and so on. But the state of computer vision, what we have right now is not that mature to capture everything in an unsupervised fashion. Yeah, obviously, yeah, that's a very interesting direction to go. But we are the techniques that we have, the models that we have are not too mature yet. So we need for now we solve the problems in a supervised fashion, and later we want to relax these constraints and go in the unsupervised direction. Yes.
While we're asking questions, so if I understand correctly, the label data you're using is this Pascal data set.
Right.
And what's the approximate size, the number of label data points?
So that data set has around like 30,000 images and like 15,000 used for training and 15,000 for testing the.
So a standard issue in machine learning, right, is if you substantially increase the amount of labeled data, these results change, and in particular, right, more complex methods don't always continue to outperform. So is that an issue for, right, you're showing as you're layering additional features and information, performance improves, but what if instead of that, I just gave you an order of magnitude more labeled data? Do you think the results would change?
Yeah, there's a chance that the results like change completely, and so if you use more training data, it might beat the model that we have. So, but in general, it's the core of intelligence is to reason about new categories and new objects based on just a few training examples. So, for example, if I show you a new object to use, and you can easily generalize that to other instances of that particular category. So it would be interesting to solve this problem with as few as with very low number of training images. Yeah, that sometimes we do not have access to that huge amount of training data. So that I think it is better to design the methods so they work with very few training images.
So along that question, so how scalable is this? So how many 3D models you can get, CAD models you can get? Are you crawling out of Google Warehouse or?
Yeah, the main source that we had was this Google 3D Warehouse, and right now we are extending that data set to 100 categories, and for each category we can find like roughly 10 CAD models. And so that means like we have like 1,000 CAD models for all of these objects in.
And you have CAD models per fine-grained category, not per actual category, right? Not for basic level category.
Yes, yeah.
And along Shishi's point, so are you thinking about some sort of knowledge transfer between them? So imagine that you will not have 3D models for all fine-grained categories of categories. For example, do you have CAD models for all the cars currently? Probably not.
No.
Then would you think that actually you would be able to infer something from some fine-grained categories for which you don't have a 3D model?
Yeah. So that's correct. So we do not have an exact model for all of the instances in Pascal dataset. But so to answer your question, yeah, that's might be. Some of the finer subcategories are very similar to each other. So maybe we can use one of those CAD models as a representative for all of those fine categories, and we might not need the very detailed information for all of those things, because there are a lot of so when you take a picture, a lot of things are blurred out, and so you don't really see the details that that you need. And so I think you can transfer knowledge between different different like finer subcategories, and a model might be good enough to represent all of these a class of finer subcategories, not just one particular instance. So, okay, so here is the data set that we use for training and evaluating our model. So this is the annotation tool that we had. So we have a number of CAD models, and each CAD model we have a set of these red dots are, we call them like key points, and ask the annotators to identify these key points and these images. And based on the these 2D, 3D correspondences, we can estimate the viewpoint, the location and orientation of the camera with respect to the object. So that's a data set that we use for to evaluate and train our model. Okay, so just to conclude this part of the talk, so we propose a course to find hierarchical model as a unified framework for object detection, 3D pose estimation, and subcategory recognition. And so the joint modeling of these tasks enable resolving ambiguities that exist in when we model these tasks independently. And also, we can model continuous viewpoint, which is not possible to do by like discrete classifiers and so on. Okay, so at the end of the talk, I will talk about like potential future work and what we can do with this machinery that I talked about. So one thing we can do is we can search for an object. So if you search for an object, it returns different pictures of that particular instance. And from these instances, you can create a 3D model of that object. And if you have the 3D model of that object, you can synthesize new scenes. You can synthesize new views. Basically, you can go from text and to kind of a new novel view of a scene. And also, another thing we can do is instead of searching for the object, we can query a certain property of that object. For example, I want to search for chairs that have flat backrest, and that's kind of a difficult problem because what does flat mean? And so we need to do some sort of mapping from the text to image and say, okay, so this concept of flat means this, and also at the same time, we need to handle the 3D pose and intra-class variation and so on and so forth. So that's a kind of difficult problem, how to go from the text space to the image space and from image space back to the text space. So, and also another thing we can do is if you check the tags for this image is like office and desk. So the tags are okay, but not really, but not rich enough. So one thing we can do with visual information is that augment these tags with additional tags and provide richer descriptions for the images that we see. So basically there is a loop that so we have the text, we can get some images based on the text, and then we can so we have these images, we can provide additional tags for that image, and then go back to the text, and so we can go back and forth between these different modalities and provide and make our description richer and richer. And the last but not the least is so as I said before, reasoning about the objects based on pixels is almost sometimes is almost impossible. So we need additional things. So we need to go beyond pixels. We need to learn common sense knowledge and to reason about that. So I guess that the reason that we can say, okay, these pixels are table pixels is the 3D geometry of the scene and other type of knowledge that does not exist in pixels. So here we know that this monitor is in a stable position, so it's basically on a flat, means that it's on like a flat surface, and we have this type of knowledge which we cannot really get from the pixels, and so that's might be an interesting direction to go and learn common sense knowledge, and that common sense knowledge might be like physics, it might be like 3D geometry of the scene and other type of modalities that we have. And yeah, finally, I'd like to thank you for listening to my presentation, and also thank my collaborators at different places.